Hello and welcome to today's episode of Kitchen Physics. I'm your host, Amanda. I'm a CPA by day and a foodie by night, and here I am doing fascinating physics in my kitchen. Let's get started. Today's physics experiment involves the energy principle. I used the energy principle to predict the temperature changes involved in the process of boiling water, to attempt to determine whether it is true that salted water boils faster, and also to see if it is true that starting with hot tap water does not make the water boil any faster. I concluded that the main effect on the total time to boiling was the starting temperature of the water, so that the hot tap water did boil faster, but none of the ingredients I added had too much effect. The energy principle states that changes in energy can only occur by processes that transfer energy from the surroundings to the system, or vice versa. For this experiment, my system was my cooking pan, my ingredients, and my candy thermometer. The surroundings included everything else, including the stove burner. I set up my experiment by measuring ingredients into my aluminum pan and adding the candy thermometer. I turned the stove burner on high. Football fans, please note that on my stove that translates to all the way turned up. I allowed the burner to heat up, then placed the pan on the stove and measured the temperature changes in 1-minute intervals. For each experiment, I also recorded the exact time that the temperature became 212 degrees Fahrenheit. For the most part, I started with a room temperature pan and ingredients except as noted. To calculate my expected results, I algebraically converted the formula for changes in thermal energy to a formula for calculating the temperature change based on the energy input. This formula takes the change in thermal energy and divides it by the mass of each ingredient times the specific heat capacity of each ingredient. For this experiment, I decided to use a spreadsheet program to calculate the predicted temperature values. I chose a spreadsheet because for this experiment, using Python would have been like swatting a fly with a sledgehammer, and also because I use spreadsheet programs extensively in my work as a CPA, and so during this class I have become very interested in the possibilities of using spreadsheets to solve physics problems. I set up the constants for the calculation at the top of the spreadsheet. My cooking pan weighs 520 grams. I chose to use a relatively small pan and relatively small amounts of ingredients in order to cut down on the total time for the experiment. I believe the cooking pan I chose is made completely of aluminum. I added 480 grams of room temperature water to the pan, which is about 2 cups of water. I started with a room temperature of 71 degrees Fahrenheit, 21.67 degrees Celsius. I looked up the specific heat capacity for water and for aluminum and entered them into the spreadsheet. I then set up a constant to represent the estimated net energy change per second. This constant is an estimated value which includes the effects of the heated burner, the mass and specific heat capacity of the candy thermometer, the heat dissipation into the air, and the fact that the pan's handle does not get hot, which means that the full 520 grams of aluminum is not being heated to the boiling point. The net energy I estimated for the calculations was 700 joules per second. I programmed a formula to calculate the predicted temperature at time intervals of 1 second. This formula took the beginning temperature of the mixture and added the net energy per second times the number of seconds, divided by the mass of each ingredient times the specific heat capacity of each ingredient. I copied the predictive formula into a table the same length as my experimental data. I then plotted my experimental data and my predicted data in a graph window. The graph matches up decently considering that there are very few experimental data points compared to the predicted data points. Some reasons for the discrepancies might be that my candy thermometer is not very accurate, that it was difficult to read with boiling water steaming up the glass, and that a single constant for the estimated energy is a gross oversimplification of the various energy changes involved in this system, that my water may not have been exactly at room temperature, and that the specific heat capacity of ingredients does not remain constant over varying temperatures. I tried the same experiment again with the following changes. I started with hot tap water, which at my house is 110 degrees Fahrenheit. I added 470 grams of water and 10 grams of table salt to approximate water for cooking pasta. I added 470 grams of water and 10 grams of white sugar, which would make pasta taste kind of funny, but in the interest of science, I needed to try it. I added 470 grams of water and 10 grams of olive oil. This combination was actually the winner in the race to 100 degrees Celsius, as expected because its specific heat capacity is the highest of any of the added ingredients I used. The olive oil also formed a film on top of the water instead of mixing with the water, which may have limited the heat dissipation due to steam. I added 470 grams of water and 10 grams of Jack Daniels. The experimental results weren't all that interesting, but the calculations had to take into account the fact that Jack Daniels is 80 proof, so its specific heat capacity needed to be a weighted average of 40% ethanol and 60% water. So the big winner in the race to 100 degrees Kelvin was the olive oil mixture. However, interestingly, all of the mixtures were actually boiling in the cooking sense at significantly lower temperatures than 100 degrees Kelvin, more like 200 degrees Fahrenheit rather than 212 degrees. This may be due to altitude or due to inaccurate calibration of my thermometer. The big winner in the race to boil was actually the hot tap water. So now you know. Start with hot tap water and you'll be eating macaroni and cheese that much faster. Thanks for watching Kitchen Physics.